So, good evening to all of you. Welcome to the 10th live session of the NPTEL course Design of Reinforced Concrete Structures. I am Sanjay Kumawat, and today I am going to solve some problems on columns subjected to biaxial bending moments with axial load. So, in the previous class, we have started some problems on columns. So, what we have seen in that class is columns which were subjected to or better I should say short columns. So we have started with the columns, and in the columns we had short columns, and those short columns were subjected to firstly what axial loads. And we have also seen that all the columns subjected to pure axial load is not ever possible. So what we actually tried to solve it for accidental eccentricity. So every column should be first checked for some accidental eccentricity, and for that value of accidental eccentricity the column should be designed, because the design of purely axial columns is very rare to see in a real time way. So today we will be seeing what is how to deal with columns which are subjected to biaxial moments with a concentrated load. So here what you can see, today we will be seeing short columns. So why short columns? Because there is something also known as slender columns or long columns, and the definitions, or better I should say the classification of these columns we have seen in the previous class, how we will be classifying these columns based upon their slenderness ratio. So for a structural components to be in the category of column, the slenderness ratio it should be between 3 to 12, and if it is less than 12 then we classify it as a short column. And when the slenderness ratio is less than 3, we classify it in the category of pedestals. And when it falls in between 12 to I think 50, so slenderness ratio if it falls in between 12 to 50, then we classify it as slender column. And above 50 we, about not 50, I think it is 120. So above 120 we do not uh, intend to uh, design a column with such a high slenderness ratio. So now let's forget everything, and let's focus on the first the topic which we are uh, present here. So in the previous class we have studied short columns with axial moments and accidental eccentricity. The second case what we have studied is a short column with with axial load and uniaxial moment. Okay, and the third case which we are going to study today is short column with axial load and biaxial moments. So the third one is the case we are going to cover today. So let's see what is it. So as you can see here, this is the cross section. This is the cross section of a structural component. This is the cross section of the column, and this cross section, when we look at it very carefully, there are two axes. So there is one axis which we call it as xx, and the axis other one we call it as yy. So how do we classify a cross section which has two axes? How do we classify these two axes into major and minor axis? Can any one of you answer me? Which one is the major axis, xx or yy? Please answer me. What? I didn't hear. Which one is the major axis?
XX.
XX is the major axis. And why do you answer XX? Is there any reason for
Uh,
XX to be a major axis?
mm, Buckling will happen around. No, YY is the major. I
YY is
think
the.
YY is the buckling will happen around YY axis.
Uh, do we classify axes as major or minor axis based upon their buckling property?
Slenderness ratio, I think.
No, slenderness ratio is the thing with the help of which we classify it as whether the column is long or short. Okay, let me answer this. So, how do we classify
The
the? Yes.
distance of a fiber from that neutral axis.
Okay, so Mithiles is saying, so are you trying to say me the higher the distance from the axis, The
yes, sir.
Okay, so you are more
So
closer to the answer which I was going to give. So the better way to say this is the axis along which the moment. Oh, sorry. So how do we classify this? Is the axis along which the moment of inertia is higher. So what is the formula of moment of inertia? BD cube by 12. So if this is B and this is D, then the moment of inertia along xx would be higher, and that is the reason the axis xx we classify it as major axis. So please remember this. So Mithilesh, what did he answer me? He answered that the higher the distance of particles from. So indirectly, that is only what is I. I is moment of inertia, which we broadly class area moment of inertia. We broadly formulate it as area into the distance of its particle, square of the distance of its particle. So the higher the distance, the higher will be moment of inertia, and that axis along which the moment of inertia is greatest, we called it as the major axis. So please remember this. So xx is the major axis and yy is the minor axis. So now I have subjected mu xx and mu yy two moments and one axial load which is acting at the center. So I have one axial moments along with two moments. So what will I say? Now this cross section is subjected to biaxial moments and a concentrated load. Again again you can see, I can take a resultant of this moment like this. So now I can say my column, it is subjected to again uniaxial moment and a concentrated load, the way you can see in this diagram here. So the resultant of these two moment will be lying somewhere here with the help of the parallelogram theorem. So as you can see now, again I can classify it as a uniaxial moment and a, but since the this is a rectangular section, my axis of bending would be something like this. Now this is the axis of bending. So now you can I bet you can't even imagine how difficult it would be to solve this problem by taking this resultant moment as the uniaxial moment and the axial load. So it would be very difficult when you take this axis as the axis of bending, and when you try to solve this problem, your neutral axis, if you find the neutral axis along this bending axis, then the neutral axis will be something like this. And now when you draw the stress diagrams, it would be again more complicated, something like this. It would not be the one which we have studied, which is parallel to this major axis. So when our cross section is subjected to biaxial moments, so it becomes very difficult to solve that problem, because the neutral axis is not parallel to our major axis. You can see it here. Now there is one another case. The case This case is of circular cross section. So what happens with circular cross section is, circular cross sections are antisymmetric in the sense, when I draw half circle and take mirror image of that, that would be exactly the other half of that cross section. That is, my cross section is antisymmetric, and because of this antisymmetric moment, suppose I take this as my major axis and this as my minor axis. Of course there is no major and minor in this case. Why? Because why there is no major and minor? Because the cross section, it is evenly distributed, or this is symmetric cross section. Now when I take resultant of two moments along the major and the minor axis, my resultant would be lying along this, and this would be the axis of bending. So you can see there is no change. So my, in case of circular cross section, what can I say? My biaxial bending moment, I can take the resultant and convert it into uniaxial moment. It would make no change. Why? Because my axis of bending is still lying along the bending axis. Okay. So when someone asks you, if you take a rectangular section, it is important to take both of the moments and solve it for the ace of simplicity. And when you uh, take the case of circular cross section, in case of circular cross section, we can take the resultant of moment and solve it as uniaxial moment. Now the most important thing, why we are looking at these concepts, because based upon this neutral axis and based upon this axis of bending, for different combinations of moments and for different combinations of axial load acting on a cross section of columns, we will be having the interaction curves. Okay, so what is interaction curve? I have already explained you this in the previous class. Interaction curves for uniaxial bending was looking something like this. So what this curve was, what was on the y-axis, it was the load P, and what was on the x-axis, it was the moment. Basically, it was P by FCK BD, and this was M by FCK BD square. So this was the interaction curves for different combination of uniaxial moments and different combinations of load. So what this curve gave me, this curve actually, it on the periphery of this curve, these are the values of the maximum moment and the axial load capacity of a given cross section, and any other cross section which lies inside this envelope, we classified it as safe cross section, or which would be safe and would not fail under that load. So this was about the uniaxial load. Now, can any one of you tell me, when we have two moments and one axial load, what kind of interaction curve will have? Can you even imagine? Here I have only one moment. I think you all must be knowing this already, because the week content of this column has already been released. So there is no like sense of making any suspense, I think. So let's see. So in case of P, M1 and M2, we won't be having a interaction curve, but we will be having an interaction surface. So that interaction surface would be looking something like this. And sorry for the diagram, let me draw it more properly. So if this is P, this is M1, and if this is M2, then my uniaxial PM1 will be this, my uniaxial PM2 will be this, and between these two, I will be having a surface. So now for P and M1 M2, I will be having P M1 M2 surface. So this is now a 3D interaction surface of PMM2. So let's first read out these points. These are very important. So you can see it here. Design of biaxial loaded column is based on an approximation of 3D interaction surface of PM x and MUY. So MUX is the ultimate capacity along major axis, and this is the ultimate moment capacity along the minor axis, and P is the uh, l- factored load which is acting actually on the column. So design of biaxially loaded column, we design it as PM1 M2 with the help of PM1 M2 curve. The interaction surface is generated as the envelope of a number of different interaction curves for different axes. I will explain you the point 2 in the next slide. Each point on the interaction surface corresponds to a value of PM1 M2 obtained from the analysis of chosen neutral axis location and orientation. So in the previous slide, I have shown you some neutral axis position and the axis of bending. So based upon those neutral axis, we get different points on the interaction curve. And the fourth point, you can understand it very easily. Region bonded within the interaction surface is safe region. Any point that lies outside the surface is unsafe. So this is similar to the point which we have covered in uniaxial and axial loaded. Any point inside the curve is safe, and any point outside the curve is not safe. The column will fail. So this is the interaction 3D interaction curve. You can see it here. P M1 P. I am trying to explain this curve before solving the problems, because you will be finding it easy when I explain you the steps first with the help of this curve. Afterwards, the problems you will be able to solve it very easily, because conceptually you should understand the things. So we have two moments M1 and M2 and an axial moments, and that is the reason we have three axes. So the first axis here is, let name it as, this is the x-axis, this is the y-axis, and this is the z-axis. So now I want answers from you guys. What does this curve in the plane zx will represent? Come on, anyone? And what will this curve in the plane zy will represent? Come on.
Sir, PM interaction curve between factored load and the moment along major axis.
Yes, exactly. I wanted you to understand this. So when you are in xz plane, you will be having a combination of p and m, and the m will be uniaxial. When you are in the plane zy or yz, for that plane, the curve which lies in this plane, it will be a curve for p and a uniaxial movement along the minor axis, and this will be along the major axis. Now when I rotate these curves and I comes come onto the surface of this curve, just feel this, what is happening. What is this happening? What does these curves in between these two planes represent?
Biaxial.
Biaxial,
Uh,
yes. Now we have both combinations of MUY and MUX. So this was important to understand. Now we have one more plane here. Can you see? This plane is XY. What does this plane gives me?
Beam bending.
Bending by only. Better way to say is XY plane, it will give me biaxial bending corresponding to a value of load. So you can see for different values of load, I will be having this biaxial combinations of moment. Did you see? Did you see what I am trying to say?
Sir, it is for beams.
No, no, this is not for beams. This is actually why you said this is for beams.
Because in the previous case we had you talked about
Yeah.
means on the x-axis it was for beams means purely
Yes, yes, yes.
uh,
Exactly. Okay, so listen first carefully what I am saying. If you talk about this curve which is lying at the bottom, is what is the value of p? P is 0. So now any structural component which has a load P equal to 0, and when it is subjected to only pure moments, then we classified that structural component into beam. So yes, you can say if my structural component, if it lies in this curve which is at the bottom where P is 0, then the component would be classified as beam. But when you come forward, when you come above this curve, there will be some value of P. See, did you see? So now this is not for beam. This is subjected to P and M1 and M2. Okay. So I'm pretty sure you all now be like imagining how difficult it would be to use this 3D interaction curve and solve a problem, or to solve a, or to design a column. So for simplicity, what we will be doing, so whatever it is written here, I have already explained you all can read it afterwards. So the most important thing, how to simplify this interaction curves and design a column. So what is code suggests us to use the xy plane of this curve. So this xy plane curve has mux and muy for a constant value of p. So if we have a factored load acting on the column, so for that factored load, what we can do, we can have biaxial, we can design the column for biaxial moments. Yes, Murugan, are you trying to say something? Okay, I think that was by mistake. So what did I say? Don't worry, or don't get scared of these 3D interaction curves. What is code says just use the xy plane of this interaction curve for a particular value of p and design the column. Okay, so now I will be showing you in the next slide how to do that. Okay, so first let's understand what are these different parameters. So what is mu? Mu is the resultant moment of mux and muy. This is the resultant moment. What is mux? Mux is the design flexural strength of the column along the major axis. Muy is along the minor axis. What is mux1? What is mux1? Mux1 is uniaxial moment along the major axis, and muy1 is the uniaxial moment along the minor axis. So now the difficult part of this problem is, let me make you all you understand what will happen here. So we have mu y1, mu x1, mu r, mu ry, and mu rx. So these two are what? These are biaxial moments along major axis and minor axis, and these are the moments, or better I should say, these are the moment loads, or these are the moments which are acting on the column. And what are these are the moment no, these are the uniaxial moment capacity. So mu y1 and mu x1 are the capacity, and these are basically the loads, if we want to broadly classify it. Okay, so now I will be showing you the simplified version of this interaction curve, with the help of which we will be designing the biaxial columns. So you can see it here. So what is this? This is one of the interaction surface. This is the xy plane. I am looking the interaction curve from the top and taking one of its curve for a particular value of p. So now what Professor Bressler says, if you satisfy this equation, so this equation, if you satisfy for a column which is subjected to a concentrated load and a biaxial moments, then the column would be safe. So while designing a column for biaxial moments and a load, you will have to satisfy this. You will have to take care of this equation according to Professor Bressler's formulation. So you can see it here. How this formula will relate us to the interaction curve is the value of alpha n, which the value of alpha n, from where we will get this alpha n we will get it from the interaction curve. So this alpha n, it is dependent upon the value of load factored factored loading capacity of this column. It is dependent on this, this is not equal. This is dependent on p puz. From where I will get this puz, we have a formula, that is the capacity of column. So this puz, it will depend upon puz, and based upon then that puz I will have an alpha n value, and based upon that alpha n value I will be selecting one of this interaction curve, as you can see it here. So for one of this interaction curve, I will have an alpha value. I will place that alpha value here, and I will see whether my equation is satisfied or not. Okay. So here you can see what all are the terms which are included in this equation. Sorry first is the mux, second is muy. So what are this? These are the uh, you can say these are the loads, moment loads, matlab the moments which are acting on the column along the major axis and the minor axis. And what are mux1 and muy1? These are what? Uniaxial moment capacity. So just keep this in mind. We are using the xy plane of the interaction curve, and in what manner we are using it? We are using it based upon the value of alpha. The value of alpha, it depends upon the factored load. How to get that factored load, I will be showing that in a minute. So based upon that factored load, you will get an alpha value. That alpha value, you put it here. If this equation satisfies, my column is safe for that biaxial moment and for that factored load. Did you get it? How we are relating this with moments and the factored load? So basically now what our task is, this mux and muy, this this will be known to us, because someone will ask me, okay, these are the two moments which are acting on the column, so please design my column. So how you will, now the question is how you will find these uniaxial capacities mu x1 and mu y1, because in the question one, it what it will be given, fck it will be given, fy it will be given, d it would be given, d dash it would be given, and what else it will be given, x it will be given, mu y will be given, and p will be given. So all of this is d. But how you will be knowing, and the cross section of that column will also be given, or you can assume it if it is not given, because that is the way in which we initiate the design of column. Suppose this is also given, so how will we find the uniaxial capacity along the major axis and the minor axis? You know what is a uniaxial? We solved the problem for mu x1 and mu y1 in the previous class. How will we find mu x1 and mu y1?
PM interaction curve.
Yes, PM interaction curve, but we have these moments along x and y direction, we have the load, we have everything, but how we will find the uniaxial capacity? We don't have the reinforcement yet, because we have designing a column means to decide the b and d of that column and to find the reinforcements. So b and d, either it is given or we will assume it, but reinforcement we don't know unless we don't. Yes, yes.
We'll choose a percentage of steel.
Okay, so that is a way Shivam is asking us to choose a percentage of reinforcement. That is, he is asking us to assume a percentage of reinforcement. But what IS code suggests us, indirectly we will be doing that only. But what IS code suggest us the more proper way to guess this percentage of steel would be what? Okay, so okay, I will be showing you this slide afterwards. So a better way, have I not included that here? Okay, I have not included. So let me just write it here only. So what IS code says, how to find the uniaxial moment capacity of that cross section. You just assume that there is a moment which is of magnitude this 1.15 times mu x square plus mu y square. So assume that a moment it is acting along a axis of major moment. So what do you mean by along the axis of major moment? Suppose we have mu x here and mu y here. So IS code says just assume a moment. Suppose mu x is higher than mu y. So IS code says assume a moment m which will be acting along a axis which contains higher moment. So this is the axis which contains higher moment. So I will assume a moment m here. Okay. So this is the way I have assumed m. So now I will be having the cross section of column. Now I have a m acting on that. I have a p. So for I don't have that p, or I have, okay, I have that p. So for that p and for that m, what can I find? I can find the reinforcement using PM interaction curve, because I have all the other things. I have fck, I have d dash by d ratio, I have the grade of steel. So based upon that, I can now find the percentage of steel, and I can distribute that steel on all the four sides of column. Okay, once I have done this, so the using the PM interaction curve, I will get this percentage of steel, and I will distribute this steel in the form of some number of bars. So this will be the which this will be the value of percentage of steel which I get from PM interaction curve, and there will be something which we call it as percentage of steel provided. So now based upon that percentage of steel which is provided, now I will be using this percentage of steel which I have provided, I will be finding mu x1 and mu y1. I hope I was clear. Mu xy and mu uy, these are the external moments which are given in the question. Mu x1 and mu y1 are the capacity which I will be finding by using this approximation method. This approximation method is given in IS code. IS code gives this method because this is the most appropriate way by which I will be designing my column. These are by various experimentations and by trial and error method. So we will have to follow this method. So afterwards, I get mu xy and mu y1 and mu x1. I will substitute all of them here, and I will check whether this is less than one. If that is less than one, I will I will what I will do, I will just say my column is safe whatever reinforcement I have provided. If this value is not less than 1, then what will I do? I will revise either the B into D, either the cross section, or I will increase the percentage of steel. So this is the trial and error way by using which we will be doing the biaxial moment design with an actual load on the column. So don't worry if you don't even understand this. I will be taking two problems, and with the help of that, I am sure you will be able to understand that. So, firstly, please remember these concepts. Anyone, no one will ask you in the interviews or at any other place like, okay, design a column for this moment and this moment. They will ask you how you use the 3D interaction curve. So what you are supposed to say, I am using the 3D interaction curve for a particular value of p. So for that particular value of p, I will be having curves which will be showing me the different values of mu and my. So for that different values of mu and my, I will satisfy the braceless formulations. If my braceless formulation is satisfied, I will declare the column to be safe. Okay, now what did I say you? My braceless curve, it is for, okay, not braceless curve, my alpha n. How to find alpha n for a particular cross section? I said you it depends upon puz. So how to find that puz? So puz, you can see it here. So why we are, okay, puz, oh, where is it? Puz. Okay, so puz, it is given by this formula. Puz is what? The capacity of my cross section. So this, don't relate it with the previous formulas which we have studied in the previous class, because these coefficients are slightly different from them. This is given in IS code. So you can find the puz, that is the axial capacity of the column which is subjected to biaxial moments. With the help of this, you will be finding the axial load, and this axial load, you will have to substitute, you will have to check the ratio of what load is coming externally divided by what is the capacity. Based upon this ratio, if my this ratio is less than zero point 0.2, then alpha 1 I will take it as 1. Between 0 to 0 0.2, my value of alpha 1 is 1, alpha n is 1. And if my ratio is in between 0 0.2 to 0 0.8, then what will I say? My alpha n will vary linearly. You can interpolate it, or the interpolation formula is given here. And if my value of this ratio in between 0 0.8 to 1, what alpha n will be 2. So based upon this alpha n value, I will have one curve from here, and based upon that alpha n value, I will substitute. So this curves is nothing but it represent this equation given by braceless. So you will have to submit alpha n here, substitute alpha n here. You can calculate mu y and mu x now. You have this value already with you, then you satisfy this. So this is the easiest way to design a column subjected to biaxial moments and concentrated load. Okay, so this I have already shown you how you can find the axial capacity. Now let's come on to the problem. So what the problem says? Any doubt, Shiva? Okay. Okay. So what does this problem says? A column having dimensions 400 by 400 and located in the lowermost story of a braced frame is subjected to a factored load of 1300 kilonewton and a moment of this and a moment of this. The unsupported length of the column is this. Okay, this is the unsupported length. Design the reinforcement in the column using grade of concrete is given, grade of steel is given. Assume the effective length ratio of the braced column is 0.85. Okay, effective length ratio they have given, and the unsupported length also they have given. Now you can find the effective length by multiplying 0.85 by 3.5. Provide an effective cover of 60 mm and use 8 mm diameters bar for providing lateral ties. So what is the very first step? Anyone? I know I have to design this column for a load and biaxial moments. This I can interpret from this question. What else I need to know before starting my design? What else I need to know? What checks I will have to give before initiating the design? Anyone? Have we studied the design of slender columns yet? Have we studied the design of slender columns? No. But is there anywhere in the question is it given whether the column is slender or short? There is, it is not given in the question. So I will have to first find whether the column is short or long. So firstly I will be finding the slenderness ratio. So calculate the slenderness ratio. What is it? L effective by least lateral dimension. So here I have a square column of 400 by 400 mm. So on both the sides my least lateral dimensions is 400. So L effective you can find it. How you will find L effective? 0.85 into 0.85 into 3.5 will be L effective. Dx and dy both are 400. After substituting that, I will get a slenderness ratio of 7.44, which is less than 12. That means my column is short. So my column is short, but it is subjected to P, Mu, and My, and that is the reason I will be using the 3D interaction curve. Before that, something else we need to check now before initiating the design. Is there anything in your mind that we should check? I have checked the slenderness already. What else I need to check before initiating the design? Come on. In the short columns, while designing the short columns, what did we check first? Of course, we check first the slenderness ratio. What was the second step in the design of short column subjected to axial load? Can there be any column which is only subjected to axial load? Is it possible to have a pure axial load on a column? Am I not audible? Hello? Am I audible? Hello?
Hello, sir. Your voice is breaking many a times.
Now, am I audible now? Hello? Am I audible now? Actually, I cannot hear you. Hello?
Yes, sir.
Am I audible now?
Yes,
Yes, sir.
yes, yeah.
Okay, okay. Sorry for. I thought no one is answering me. So, what I was saying is, so did you follow me up to these three steps? Did you all follow me? Shivam, can you unmute yourself? Arey, yaar. Hello? Hello?
So not getting your voice.
Now am I audible?
Yes, sir. It breaks a lot in between the videos.
Let me connect it to some other device. Just wait for some time.
So video is also not continuous, sir. It's getting break.
Yeah, yeah. Sorry about that. But don't worry, you will be receiving my video on YouTube. Huh? Hello, am I audible now? Hello, hello.
Yes, sir. Yeah, it's audible.
Sorry, guys. Can you hear me?
Yes, sir.
Okay. Let's resume my session. So, what I was saying, firstly, before initiating the design of columns, we will have to check whether the column is short or long. So, how to check that? I will find the slenderness ratio, and the slenderness ratio it is falling below 12, and that is the reason I am classifying it as short column. Now, what I was asking you what is what else should I check before initiating the design? I have checked the slenderness ratio. What is the other thing that I should check first?
D dash by D.
D dash by D. What will I get from that? D dash by D, it will be useful for finding the for finding which curve we should use, which interaction curve we should use. Okay, that is fine. uh, I explained you previously, is it possible that any column, can I design any column which is subjected to pure axial load? Is it possible?
Minimum eccentricity we
Okay,
have to
yeah.
find.
So before initiating any design of column, you should first see whether it is a long column or a short column. The second step is to check the minimum eccentricity value, because we never intend to design a column for zero eccentricity. There is always a check for accidental eccentricity. So that accidental eccentricity we used to calculate it with the help of a formula which I shared with you in the previous session. That formula was given by, okay, sorry, I just broke the suspense. That is fine. But that formula it was given by something d by 5. No. What it was? D by 30 plus something by 500. This was the accidental eccentricity value, and this or 20 minimum of this two value I have to take. Okay, so this is the accidental eccentricity. This eccentricity I should compare it with the eccentricity of my column. So how you will find the eccentricity of this column? This is subjected to mu x and mu y, that is for sure, because the mu x and mu y are given as 190 and 110. Now how you will find the value of eccentricity for this column? Come on.
Sir, in E minimum in x direction and E minimum in y direction we will
Yeah,
take.
that is fine. That is the excellent accidental eccentricity, and both of them would be same because this is a square cross section. That is fine. What I am saying, just
0.05d. If it is any of them is greater than 0.05d, then we'll go for biaxial bending.
yes, yes, I know what you are saying. You are all of these answers you are saying is for finding the accidental eccentricity. Listen carefully what I am saying. This keep this accidental eccentricity apart. I am asking how to find the eccentricity corresponding to these moments. These moments are already acting on my column, but now I am interested to find what is the value of eccentricity because of which these moments are coming. Did you get my question? How you will find? This is also subjected to a load of P. Did you get my question? What is the value of Ex and Ey because of this? The moments Mux and Muy are coming onto this square column 400. Yes, who was that? Okay, so let me answer you. See, whenever a, whenever a structural component is subjected to some moment, that moment is actually not a moment. That is a load which is acting at some distance E. So now what I am doing, I am transforming this section into a concentric load P and a moment. With that moment value will be PE. Did you see what I am saying? So if someone is giving you a moment value has 190 and 110, those moment values are coming from P into E. P into EY would be MUY and P into EX is MUX. Did you understand? So
Yes, sir.
how we will be finding the eccentricity is this. Okay, so these are the eccentricities because of which the moments Mux and Muy are coming onto the column. Now these eccentricities are to be compared with the accidental eccentricity. Okay, so the accidental eccentricity is calculated by using this formula. So it is coming out to be 20.33. So accidental eccentricity is 20.33, while the actual eccentricity which is acting on the column is 146 and 84. So that is fine. I will be now going for the moments Mux and Muy because my eccentricity which are actually acting on the column, they are greater than the accidental eccentricity. Now I will ask you one question. What if this value of minimum eccentricity is coming out to be greater than the eccentricities which are acting on my column? Then what will I be doing?
We have to limit the eccentricities.
We have to limit the eccentricities. Okay, so you are saying if I have an accidental eccentricity which is greater than, but I cannot limit that eccentricity. Like this would be a way. How can I limit the eccentricity? See, let me first think what you are trying to say. You are saying me to limit the eccentricities. So if I have x minimum and ey minimum value greater than what is acting on that, okay, so it is already limited. Murugan, if you see, if my ex and ey values are less than e minimum, that is the accidental eccentricity, then these are the actual eccentricities and this is the accidental eccentricity. So the actual eccentricity is already less, that is the eccentricities are already limited. But what is code says us, is code says us to design the column for this minimum accidental eccentricity. This is the provision. Did you get me what I am trying to say? Yes.
Then we have to take the EX and EY actual eccentricities, sir.
Can you repeat please?
We have to consider the actual eccentricities along X and along Y.
Okay, so what Murugan is trying to say, he is saying if IS code asks us to design for a minimum eccentricity of this value, that is the accidental eccentricity, and if these are the eccentricities which are actually acting on the column, but IS code says us to design it for accidental eccentricity. So what will I do? I will consider this accidental eccentricity because accidental eccentricity is greater than the actual eccentricities. So I will recalculate my moments. How will I recalculate my moments? I will not use MUX and MUY now. I will use P into EX minimum. I will modify my MUX as EX minimum into P, and MUY has EY minimum into P. So whichever is the greater value of eccentricity, that value of eccentricity I will use to design my column. If there is any doubt, you can ask me right now only, or everything was clear.
Sir, here Ex is like the applied eccentricity. It is 146. So we have to consider this one.
See, now we have to consider this one because this value is greater than the accidental eccentricity. See,
Yes.
what IS code says us, it says us even if the column is having a concentrated load, if it even if the column is subjected to a purely axial concentrated load, then also we have to design it for a minimum eccentricity of 20, even if it is subjected, because this is the accidental eccentricity we have to take. But now I just gave you an case, what if the accidental eccentricity is greater than the actual eccentricity which is to which the column is subjected. But IS code says us to design for accidental eccentricity, so we have to design for that accidental eccentricity, because this provisions, it comes from lot of experiences and researches and experiments and from trial and error. So based upon this clauses, if we follow these clauses, my column would be safe for any type of eccentricity which comes on it. So I have to follow this strictly. I have to design this for accidental eccentricity if it comes out to be greater than the actual eccentricity. Okay, I hope this was clear. You can like rewind this clip again and like satisfy yourself what I was trying to say. For the time being, I would like to go further with this problem. So I have checked the eccentricity, I have checked the slenderness ratio. Now I will begin up with the design of the column subjected to biaxial moment. So of course we know, what I need to find mu x1 and mu y1, the uniaxial moment capacity. So for that purpose, what we have seen, I will have to assume a moment which is of magnitude this, and this moment we will assume it to be acting along the axis which is subjected along an axis of major moment. So which is the major moment, mux or muy? Which is the major moment?
MUX.
Mux is the major.
MH.
Okay, so mux is the major moment, and that is the reason I will assume it to be acting on the axis where mux is acting. So I will write m here. So this is for this m. I will assume my column to be subjected to this m and a load of pu, which is already given in the question. And now I will design this column as a uniaxial moment. So I will now find the reinforcement using the design chart. All other values are already given. I have just assumed a moment value. So that moment value was just a approximation. So for that moment value, now I will be finding the percentage of steel using the interaction curve. So here you can see, for a value of 3.325 and for a value of 0.156, I will get a percentage of steel around 0.14. It is not the percentage of steel but the ratio of percentage of steel by FCK as 0.14. And now multiplying by FCK, I can get the percentage of steel. So, and the percentage of steel, it can be converted into the area of steel by multiplying it with the cross section. So this is the area of reinforcement. Now I will provide this reinforcement on all the four sides. So I have provided 12 bars of 25 mm. So now these 12 bars of 25 mm will correspond to a area of steel which is 5892 greater than which is required. So again I will find the percentage of steel. So this is 3.68 percentage of steel. What I will do now, based upon this percentage of steel and based upon the other values which we already know, this will be constant for all the trials, but now my percentage of steel has changed. So based upon this percentage of steel I will find mu x1 and mu y1. Again I will go to the charts, I will see what percentage of steel. Okay, so what will I do, I will just divide this by f. So here I have already done. So I will be seeing which curve. So let's look at this curve. So which curve it corresponds to 0.15. So corresponding to that curve and corresponding to a value of pu by fck, I will have a value of moment. So that moment I will get it from here. So now since my column is square, it is a square column, that's why d dash by d it will remain same, pu it will remain same, and percentage of steel it is already same. So that's why my mu x1 and mu y1 are equal. So again a question for you guys, what if my section was not equal? So I will get one value of mu x1 because my moment was acting along. How will I get mu y1 if my section was not square? Come on, answer me. It is easy now.
It's axial load into eccentricity along y-axis.
Yeah.
EY. Actual EY.
So we have to consider now the other. What will I will have to use the other interaction curve which will correspond to. So here d dash by d it was constant for both the side, but if my d and b are not equal, then I will have to use an other interaction curve. So for that interaction curve I will be finding the other value, that is mu y1. So I hope you understand. So now I have mu x1, I have mu y1. What I need is alpha n. So alpha n, for finding alpha n I will be needing the axial capacity puz. So puz you can find it easily. I request you guys to please once again go through this video so that you will be clearer with the concepts of biaxial moment and axial load design of columns. So here is the ratio of pu which falls in between zero point 0.2 to zero point 0.8. So we will have to do the linear interpolation, and with the help of that linear interpolation I am getting a value of alpha n as 1.274. Now when I substitute all of this in this equation I am getting 0.986 which is less than 1. Hence my column is safe for the given percentage of steel which I have provided across the cross section. Okay. Now finally, this is similar to that of uniaxial or the short columns. I will have to provide ties. So the provisions for ties are as follows. So you can provide it. Now finally, the detailing. So detailing here you can see it. The bars I have provided 12 25 mm. So this was very, if you go through this video again you will also find it easy, and this is not very tough. I have tried to explain my level best, and you can again go through this video. So I have a problem too also, this you can solve it by your own. I have not brought the solution for this. I only have the steps for it, but don't I have not calculated the value. So in this also has a similar manner question, but now this is a rectangular cross section column. I have already discussed what if my column is having a rectangular, what all changes we will have. I have discussed in the previous problem. I have the mux, I have muy, I have the load, then effective lx and ly are already given, grade of concrete is given, and fe415 is given. So in the similar fashion, first check the eccentricities. Slenderness you have to check it, you check it by your own. I have checked first the accidental eccentricity. If the accidental eccentricity it comes out to be greater, then I will have to modify these moments. If the accidental eccentricity falls less than the eccentricity actually acting on the column, then I will use the moments which are given in the question. Then what I will do, I will find mu subject it to the major moment axis and find the percentage of steel. Then based upon that percentage of steel I will provide the number of bars and that number of bars will correspond to a certain percentage of steel again, and based upon that percentage of steel I will have mu x1 and mu y1. Okay, so after I find the mu x1 and mu y1, I will check using the Blazer's formula whether my column is safe or not. Okay, then provide the transfer style and finally the detailing. So this was all about today's session, what I had planned to teach today. And if you all have any doubt, you can ask me now or you can go through this video again. So the floor is open for you all to ask me any questions regarding today's class. Huh? Don't just randomly ask me some questions. Any questions? Am I not audible?
No questions, sir.
No questions. So in that case, Mithilesh, do you have any question? Okay, so Mithilesh is not audible, but I'm assuming he has no questions. Even if you have, you can come to me in the next class. So, in that case, I would like to conclude this class, and better you see this video again and clear your concepts. So I will see you in the next live sessions on the next Tuesday, where we will discuss on the design of footings. So we have two classes left. Both the classes I will be focusing on design of footing, and if we have time I will also use some basics of staircase design. So that was all I would like to discuss with you guys. So okay, then thank you. You all can leave now.